Salam and peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. And in this part of our journey, you and I are going to do something very special. We are going to return to an idea we met before, in part 18, and we are going to look at it again with new eyes. Before we dive in, let us repeat our short language mantra together, so your whole body remembers the code we are learning. There is one field called phi, spelled Phi. Phi is the holophase, a cyclic rhythm defined at every point in the universe. Its first echoes give us three simultaneous voices: time, which we call omega, spelled Omega, space, which we call k, and motion, which we call v, built from both omega and k. Above them, higher echoes form a branching tree that in principle goes on forever. Every law of nature is a pattern in this tree of derivatives of phi. Today, in part 21, we zoom again into the branch where knots, loops, and defects live. We first visited this branch in part 18. There we asked, how can a single continuous field, this rhythm phi, give us things that seem solid and countable, like particles and charges? We answered with an image. Not new stuff, but knots in the pattern. Now we come back to that same branch with more of the language under our belt. We have met omega, the ticking of time in the code, k, the weave of space, d phi, the unified change, v, the motion echo, and even alpha, curvature, and other second-level accents. We have seen waves and activity, and how information can ride on patterns. With all of that in our hands, we now return to the knots and ask a deeper question. What if these knots in phi are not just curiosities, but the actual building blocks of matter? That is the heart of part 21. Let us start with a gentle rewind to part 18, but in a way that feels like a story rather than a lecture. Imagine you are sitting on the floor with a long rope in your hands. It is soft, flexible, and completely unremarkable. You hold both ends and stretch it so it lies straight. This is our smooth phi, a phase field with no surprises. Every point along it has a value, like the hand of a clock pointing somewhere. But the way it changes from one point to the next is calm, simple, easy. Now, without adding anything new, you slowly tie an overhand knot in the rope and pull it tight. You have not created new material. You have not changed the fiber. All you have done is rearrange what was already there. Look at the rope again. If someone walked into the room and saw only the middle part, they would say, there is a knot. Something has happened there. That part is different. But if they zoomed in all the way to the level of the fibers, it is the same rope as everywhere else. This is the first key memory from part 18. A knot is not a new substance. It is a stable pattern, an arrangement that cannot be undone without cutting. You can push the knot around. You can tighten it, loosen it a little, slide it along the rope. But unless you cheat and let the rope pass through itself, the fact that it is knotted does not go away. Knotted versus not knotted is a property that survives all gentle changes. We call this kind of property topological. You did not need the fancy word, you felt the idea. Your coffee mug and a donut are the same in this sense. Both have one hole. A plate has none. You can stretch, bend, and twist, but you cannot change the number of holes without tearing. Then we invited you to imagine phi not as a rope, but as a field spread throughout space, with a little arrow at each point, or a little clock hand that can point in any direction from 0 degrees to 360 degrees. As you move through space, this arrow can rotate. In part 18, we ask you to walk around the loop in space. At every step, you look at the local phi arrow. You count how many times it turns as you make one full circle. If it turns once, we say the winding number is +1. If it turns backwards once, that is -1. If there is no net turn, that is 0. And the surprise was this. As long as phi stays smooth along your loop, that winding number stays the same. You can jiggle the pattern, shake it, stretch it, but you cannot change the count without doing something violent, like letting a defect pass through the loop. We gathered all the places where phi cannot be made smooth into a set called sigma, spelled S-I-G-M-A. You can think of sigma as the defect skeleton of the universe, the hidden lines and points and surfaces around which phi is allowed to twist in non-trivial ways. That was part 18. There, we stopped at the level of shape. We said, these windings are like knots and vortices. They are robust. They behave in many real systems like discrete, conserved things. Now, in part 21, we take the next step. We say, what if these topological patterns are not just passively sitting in phi, but are what we have been calling particles and charges all along? Let us make this shift slowly and kindly. Imagine now that the rope with knots is not a rope on your floor, but the fabric of the universe itself. Suppose every knot you tie in that rope is like a particle, an electron, a vortex, some stable chunk of reality. How would you know if that picture is any good? You would look for three things. First, you would check whether these knots are stable. Do they survive gentle disturbances, or do they fall apart at the slightest touch? A real particle lives a long time, or at least a predictable time. It can move, scatter, be pushed, but it does not instantly dissolve. Second, you would check whether they are countable. Can you have one, two, three of them? Can you say this region has charge +1 and that region has charge -1, and treat those labels like integers that add and subtract? Third, you would check whether they interact in ways that look like the interactions of particles. Do two opposite knots cancel each other when they meet, like matter and antimatter annihilating? Do two similar knots merge into a bigger knot, like charges adding up? Now go back to what we already know about windings in phi. A winding number is robust. You cannot change it gradually. It is countable. It is an integer. And when two defects approach, their windings can add or subtract, just like charges. Already the match is suspiciously good. In the Holophase picture, each stable defect in sigma with a given winding number is an atom of phi language. It is a basic noun. +1 defect, -1 defect, +2 defect, these are like the alphabet of particles. To see this more clearly, let us switch to a game. Picture a table where children are playing with marbles. Red marbles represent +1. Blue marbles represent -1. The rule of the game is simple. Red and blue together can cancel and disappear. Red and red can merge into a double red that counts as +2. You, as the referee, never see any new kind of marble appear out of nowhere. You only see red and blue being rearranged, merged, or cancelled according to simple counting rules. If we look inside the marbles with a magic microscope, we discover that each marble is not a separate brick, but a little knot in a continuous thread that has been tied in different ways. The color of the marble corresponds to the way the knot twists, clockwise or anti-clockwise. The number of marbles corresponds to how many twists we have. In holophase language, the continuous thread is phi. The knots in it are defects in sigma. The red and blue marbles are the signs of their winding numbers. And the rules of the children's game, add, subtract, cancel, are simply the arithmetic of those topological numbers. Now think of physics experiments. When an electron meets a positron, they can annihilate, leaving behind light. In the topological picture, that looks very much like a +1 defect meeting a -1 defect. The knots cancel, the field relaxes to a smooth configuration, and the energy held in that twist is released as wave-like activity. I'm not saying that all of particle physics is literally knots in a rope. The actual mathematical structures are more subtle, higher dimensional, and quantum in nature. But at the level of the holophase story we are telling together, the analogy is precise enough to guide your intuition. The message is this. Part 18 taught you that phi can form knots. Part 21 tells you that many of the things we call particles and charges can be understood as those knots. To make this more vivid, let us walk again around the whirlpool. You are standing by a sink full of water. You pull the plug. A vortex forms. The water spins around the central core and drains. You drop a tiny leaf on the surface and watch it circle around. From far away, you just see a little spinning patch of water. It is tempting to call the whole thing a whirlpool, as if it were a solid object. But what is it really? It is not made of special whirlpool stuff. It is a pattern in the motion of the water. Now imagine that water is the holophase field phi, and the direction of the flow is related to how phi winds around the central line. The line at the center, where the regular flow description breaks down, is part of sigma. Around it, the phase is twisted. If the total twist around that line is one full turn, we call it a vortex of strength 1. If it is 2 full turns, we call it strength 2. You cannot change the strength from 1 to 1.5 by gentle stirring. It jumps between integer values. This is precisely what is observed in real superfluids and superconductors. The circulation and magnetic flux are quantized. They come in whole chunks, not arbitrary fractions. Those chunks are the winding numbers of an underlying phase. Holophase simply says, do not treat this as a curious detail of special materials. Treat it as a direct demonstration that the universe naturally writes certain properties, like vorticity, flux, and charge, in topological letters. In this view, a charged particle is like a very special, very small whirlpool in the abstract phase fabric, a little place where phi twists in a way that cannot be undone without a topological event. Now, because this series is not just poetry, but a falsifiable program, we must pause and ask, how can this be tested? Take a thin ring of superconducting material. Inside, the electrons pair up and behave like a single coherent phase. Around the ring, this phase must return to the same value after a full loop. The allowed patterns of phi are labeled by an integer: 0 twist, 1 twist, 2 twists, and so on. Experimentally, each twist corresponds to a certain current flowing around the ring and a certain magnetic flux threading the center. When experimentalists measure that flux, they find it does not vary smoothly. It jumps in discrete, identical steps. Those steps are the fingerprints of the winding number. Now imagine gently changing the conditions, heating the ring a little, shaking it, applying small fields. As long as the superconducting state persists, the integer label does not drift. It stays fixed. Only when you push the system hard enough to destroy the coherence does the topological label change. This behavior is exactly what you would expect if something like the Holophase story is true for that system: a phase field with defects and integer windings. The Holophase program claims something bold but clear. The same style of explanation can, in principle, be extended to the fundamental particles and charges of nature. They too could be knots in a deeper phase field, with observable properties tied to winding numbers around elements of sigma. It is not enough to say this as a pretty idea. One has to write down precise models, compute their predictions, and see whether they match experiments. That is the hard work of the technical papers. But in this audio journey, what I want you to feel is that the bridge between whirlpool in a sink and electron charge is not mystical. It is a matter of taking the idea of topological defect seriously as the core alphabet of matter. Let us widen the picture. So far, we have mostly talked about one type of defect, something like a line you can walk around, like the axis of a whirlpool. In three-dimensional space, sigma can have different shapes. You can have point defects, little specks in space such that any loop that encloses the speck picks up a twist in phi. These behave like isolated particles. They sit at locations, they can move, and the phase around them wraps in characteristic ways. You can have line defects, threads running through space, like cosmic strings, vortices, or dislocations in crystals. If you loop around the thread, phi wins. If your loop misses it, nothing special happens. You can have sheet defects, surfaces across which phi jumps or flips in some controlled way. These behave like walls, domain boundaries between different phases of phi on each side. You do not need to memorize the catalog. It is enough to remember that sigma is not just one thing. It is a menu of possible bones inside the phase fabric, and around each kind of bone, different topological windings can live. In the Holophase codex, all of these are organized as different letters in the topological alphabet. A certain pattern of winding around the point might correspond to one kind of particle. A different pattern of winding around the line might correspond to a flux tube. A jump across a surface might correspond to a domain wall. But again, at the deepest level, they are not separate substances. They are all combinations of one underlying rhythm, phi. To help this settle in your intuition, let us walk through some scenes from daily life and quietly translate them into Holophase language. You are drinking tea from a mug. You notice the handle. It is a loop, a hole in the shape of the object. Topologically, your mug is like a donut. In the Holophase picture, such holes can be places around which phase patterns can wind. A certain field configuration could loop around that handle and carry a definite winding number. Your everyday mug becomes, in imagination, a little stage on which phase knots could live. Later, you see a smoke ring drifting through the air, perhaps in a slow-motion video. It looks like a solid ring, but you know it is just air in motion. In Holophase terms, you could imagine that the velocity field of the air is tied to how phi changes in space, and the smoke ring is a moving defect loop in sigma. It is a topological pattern, not a separate thing. It can scatter, break up, or merge with another ring, all following rules that look like the grammar of defects. You look up at the sky and notice a cyclone in weather maps, a big spiral of cloud. Again, You see a familiar topological pattern, a large-scale vortex. In Holophase eyes, you see phi twisting over thousands of kilometers, a macro-scale echo of the same kind of structure that might exist at the quantum scale. Finally, you look at your own hand. You see the spiral in your fingerprint, the loops of your veins, the branching of your nerves. All of these are geometric and topological structures in biological tissue. Underneath, at the level of physics, there are fields and phases and defects shaping how matter arranges itself. Your body is not a pile of bricks. It is a tapestry of organized patterns, many of which can be captured as stable configurations in the phase code. In all these scenes, the same idea repeats. There is one continuous medium, and there are stable, countable, topologically protected patterns living inside it. Holophase takes this idea and says, make that medium phi, and make those patterns the fundamental words of reality. Before we close, let us spend a little more time with the idea of testing, because falsifiability is the heartbeat of this entire journey. Without tests, all of this would be just a beautiful story. With tests, it becomes a candidate description of reality. Imagine a laboratory where you can shape and measure waves very precisely. It could be a tank of water, a piece of vibrating metal, a cloud of ultra-cold atoms, or an optical setup with laser beams. In all of these, there is some quantity that behaves like a phase, a direction on a circle, a cyclic state that repeats every full turn. The holophase way to think about such a lab is simple. Treat that phase as a little fragment of phi and look for sigma, the defect skeleton. Can you create vortices, knots, or domain walls? Can you measure how many times the phase winds around them? Can you see that those winding numbers stay fixed under gentle changes and only change in jumps when something dramatic happens? You could imagine one very clear experiment. You create a vortex and track it over time. You disturb the system with noise and small pushes. You ask, does the vortex survive as a recognizable structure? Does its winding number remain 1 until the vortex dies in a clear event, like hitting a boundary or meeting an opposite vortex? Then you repeat the game with a vortex and an antivortex, and watch whether they spiral together and annihilate, leaving behind only waves. In many real systems, this is exactly what happens. Quantized vortices and flux tubes live, move, and annihilate in just this way. Each one carries an integer label that does not drift. It jumps only when the underlying order breaks or when defects meet and cancel. Those jumps and that stability are the fingerprints of topology. From this point of view, every time a laboratory somewhere measures a quantized vortex, a flux quantum, or topological defect, it is providing one more hint that the universe likes to speak in this language of knots and windings. It does not prove the holophase model by itself, but it narrows the gap between the poetic image and empirical reality. There is also a personal test you can perform, not with machines, but with attention. As you go through your day, notice how often you label things as if they were little independent objects. This stone, that car, this thought, that feeling. Then deliberately try, just for a moment each time, to see them as patterns. A certain way that matter, energy, and information are arranged and moving. Ask yourself, could this too be understood as a kind of knot or wave in a deeper field? This inner experiment does not replace physics, but it trains your intuition to live comfortably in a world where things are patterns, not bricks. When new scientific results appear that point toward fields, phases, and topology, your mind will not resist them. It will recognize them as refinements of a picture you already hold. In a way, part 18 and part 21 are like two hands working together. Part 18 takes your hand and says, look, here is a rope, here is a knot, here is a whirlpool, here is a hole in a surface. Feel how some properties stay the same, no matter how you stretch and shake. It introduces the raw topological intuition. Part 21 takes your other hand and says, now let us walk back over the same terrain, but this time we will dare to say that these knots and vortices are not just fun shapes. They are the candidates for the very objects you have always called particles and charges. It transforms topology from background scenery into the main cast. Together, they prepare you for what comes next, a view of forces, geometry, information, and even meaning as higher-level grammar in the same phase language. As we near the end of part 21, let us connect this back to the master tree of phase and its derivatives. At the base of the tree is phi itself, the holophase, the silent but ever-present rhythm. The first branches give us omega, k, d phi, and v, the way phi changes in time, in space, and along motion. Higher branches give us curvature, convergence, second and third derivatives, the fine accents of the language. The branch we are exploring now carries the label sigma and its winding numbers. It is a branch that does not add a new derivative symbol to the tree, but rather asks a new kind of question about the patterns already there. Given the way phi and its derivatives behave in some region, does the configuration belong to a trivial topological class, one that can be smoothed away, or does it carry a non-zero winding, a knot that cannot be undone? The answer to that question is a discrete label: 0, +1, -1, +2, and so on. Those labels do not change easily. They behave like charges and particle numbers. That is why this branch is where matter, in the sense of stable things, first enters the holophase language. Part 18 gave you the intuition: knots, loops, holes, and winding numbers. Part 21 promotes those knots to citizens of the universe. It says, what you have been calling a particle might, at a deeper level, be nothing other than a holophase defect with a particular winding code. As you finish listening to this part, I invite you to carry a very simple question with you through your day. When I see a thing, am I willing, even for a moment, to see it not as a little brick, but as a pattern in a field? When you stir your tea, watch the tiny swirl and think, there goes a little piece of sigma. When you see two drops of water meet and merge, think of two patterns combining their winding. When you see a light switch turn on and feel the flow of current, imagine invisible phase twists organizing themselves along the wires. This is not just a poetic overlay. It is a disciplined way of seeing, one that can and must be tested in experiments. But for you as a listener on this journey, the first step is to let your intuition reshape itself. Reality, in the holophase view, is not made of separate objects floating in empty space. It is one continuous rhythm, phi, writing countless stable words in its own language: waves, knots, particles, charges, fields, and eventually, minds. In the next part, we will take this picture of knots as matter and ask, how do these topological worlds move and influence each other? How do forces and geometry emerge from the curvature and gradients of phi around these defects? For now, take a breath, look around you, and feel, even if only as a possibility, that everything you see might be a sentence written in one cosmic script. You are not outside that sentence. You are one of its most intricate words. Carry this question with you like a small lantern. What if every sound, every color, every touch is just phi, speaking softly through a different stable pattern of its own rhythm to you? Peace be upon you until the next part of our journey together.